And of course, there's been many other papers after this as well, but I haven't listed it because that was a key paper. All right. So when we are studying observers, obviously we define an error, which is the difference between what we want and we estimate. And by considering the observer dynamics and the state and the system dynamics, we can write the error dynamics. Now, this is a theorem that is reported in literature, so it's already well known. For this error to be stable, error dynamics to be stable, the necessary and sufficient condition is that this term here need to be 0, and this term here need to be 0. So we left with E dot equals NE, and then obviously N need to have eigenvalues on the left half of the S plane. So this is a result that is already published, and the functional observer design algorithms are all about trying to find the observer parameters so that these three conditions are satisfied. So all the reported functional observer algorithms do that. They provide a procedure for finding the observer matrix parameters so that these three conditions are satisfied. Now, the work of Duraj. Duraj presented, I think, the most complete theorem to solve those those equations. And his theorem states this: error approaches 0 asymptotically for any initial conditions and any u, if and only if these two conditions are satisfied. So if these two conditions are satisfied, we can design an R-order observer. So the observer that he proposed is a fixed order observer. And the order of the observer is R. R being the number of functions that you estimate. In other words, the number of rows in L. Right? So this is an if and only if condition for designing an R-order observer. If the conditions are not satisfied, the question is, if the conditions are not satisfied, then does it mean we can't design an observer? Does it mean there is no R+1 order observer, R+2 order observer? Because this theorem only states the existence of an R order observer. So this is where our work came in. Is okay, if these conditions are not satisfied, that doesn't mean an observer doesn't exist. Observer may still exist. And how do we find the minimum order observer? In other words, how do we find the smallest L that will satisfy those equations? L is the functions that we want to estimate, right? So if an R order observer doesn't exist, what do we do? That's the important question. So what we done is we just changed the problem statement a little bit. We said, okay, let's say ZT is not what we want to estimate. Let's say Z naught T is what we want to estimate, which is equal to L naught XT. That's what we want to estimate. Now, if condition 1 and condition 2 cannot be satisfied for L equal to L naught, so L is now a variable. So if condition 1 and 2 cannot be satisfied for L equal to L naught, then we need to find L, which is something bigger than L naught. Right? So L will include all the rows of L naught and possibly more. Now, with that, I think we can define functional observability. We can say if we can find a L that satisfies condition 1 and condition 2, then the triple ACL naught is functional observable. if we can find an L. Of course, L has L naught in it. Now, if we can find the minimum dimension matrix L that satisfies condition 1 and 2, then we have found the minimum mode observer. Right? Because the order of the observer is simply the number of rows in L. Okay, this is a definition for functional observability. So we're not talking in terms of a pair anymore. We're talking in terms of triple. And obviously, if L naught is I, then this definition reduces to the state observability definition. So the triple AC L naught is functional observable if and only if there exists an L in this space Rn times n. So we can search the whole n-dimensional space such that the row space of L is a superset of the row space of L naught, and L satisfies condition 1 and 2. Right? So that this condition here guarantees that L includes L naught. And if L naught, or if L equal to I, we can clearly see this rank on the right hand side is n. Rank on the left hand side is also n. So that condition is automatically satisfied if L is equal to I. L equals I means this is n. And if L is equal to I, you have a psi minus a. So this here reduces to rank